Hi everyone, good morning. Let's wait for few more minutes before starting, okay?
Good morning, ma'am.
Good morning, ma'am. Yes, ma'am.
So good morning. So for this week, we'll be looking more into like how to implement Boolean function using decoder, multiplexer, and also lookup tables. And then we will have topics like ripple carry, adder, and comparator, and so on. Okay. So starting with implementing the Boolean function using. So we'll be implementing Boolean function using decoder. So we have already seen what is decoder, right? So can anyone tell me, like, very briefly, like, how to design a decoder, or what do you think a decoder is? Maybe you can take an example of 3 is to 8 decoder. You can just tell me how to design, or what are the signals that are required for 3 is to 8 decoder.
Like in 3 to 8 decoder, we are giving three inputs and getting eight unique outputs.
Yes. And how do you select the outputs?
Through the enable pin.
Yes, correct. Great.
Yes,
Okay.
sir.
So, for here, Boolean function, let's use a three input XOR gate. Okay, three input XOR gate. So, for that, you have A, B, C. So, this will be your MSB and this will be your LSB. So, here you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 1, 1, 1. So now, and for XOR gate, we have output 0, 1, 1, 0, 1, 0, 0, 1. Okay, so this is our XOR 3, 3 input XOR gate. So now for this, if you have to write in terms of min terms, so what is it? Your min term M will be 1, 2, 4 and 7, right? And we know that if we are trying to use a 3 is to 8 decoder, so why do we have 3 is to 8 decoder? It is n is to 2 power n decoder. So our n, here we have 3, so 3 is to 8 decoder. Then what do you have? You can tell that your y of k will be equal to enable, right? Your enable and m of k. So that's how you will select your outputs. So similarly, now if you see, if you're trying to draw the circuit diagram for this, so you have a 3 is to 8 decoder. So for 3 is to 8 decoder, you need an enable, right? You need an enable connected to 1. It is connected to 1. And now here you have 1, 2, 3, 4, 5, 6, 7, 8. So this is your 8 outputs. And now here this will be your select lines S1, 2 and S3. If you see, the LSB will be C. A, B, C. This is your MSB, most significant bit and least significant bit. Now here comes the part where what do you have? Where is here? So you have terms like 1, 2, 4 and 7. So how do you write? This is your 0, 1, 2, 3, 4, 5, 6 and 7. So here you have 1 and 2. You have an OR gate. That's how you write, right? Usually how do you write? You will write OR. So this is what? Sum of products, right? So you OR. Sum is OR. So we have 1, 2 and 4, 7. 4 and 7. So this will be your 2 gate and this again will be made an OR because we are using 2 input OR gates. So this will give you Y XOR 3. So using this way you'll be able to implement any Boolean function using decoder. How? Because every Boolean function can be written in terms of min terms, right? If any Boolean function, it can be written in terms of min terms, and once you get the min terms of which is required, you can subsequently draw the circuit diagram using the decoder. Okay, so let's say you have another example where you have y is equal to let's say m of, or let me just write here, yeah, here. So if I'm writing a y here with m 0 0 1 1 1 0 0 0. Okay, so what is the min terms for y here? 2, 3 and 4. So now the same thing if I'm trying to do for 2, 3, 4, you can either write here or you can also write here. Yeah, okay, you can just write it here. So it is for 2, 3 and 4, right? So here you have 2, 3. So here you have 2, then you have your 3, and then finally this one you will have an OR with 4. So what will this give you? This will give you 1. So any function, if you're having any other function, which you can just keep on adding it like this. But now comes the question that here there are already so many gates, right? You cannot just keep on adding all the OR gates. It will just not be efficient, right? It will not be cost efficient, and also time. If there are any delays for the gates, then that will cost you more time. So here what will happen is, what we will try to do is, if you see, your XOR 3, what was it? It was M1, M2, it was M4 and M7. And your Y, just Y was M2, M3, and M4. So if you see in both the equations here, you have M2, M4. So you can use the same OR output, right? If you do first, if you have XOR 3, and if you have M2 plus M4 done, and then if you go and do M1, M7 and add it, the same M2, M4 can be used for Y also, because Y also have M2 plus M4, and this will be done with M3. So if you do it in this way, then so if you do that, you have your 3 is to 8 decoder, then you have your enable, we are giving it high, and then you have A, most significant with A, B, and C. You have to always be sure of what is this lines, because based on this the outputs are here, right? So because if you given C here, what will happen? The entire thing will change, because now here you will go like this 0 0 0 0 1. So your C will change 0 1. But if you give C here instead of A, then the entire truth table will change for this particular question. So here same 1 2 3 4 5 6 7 and 8. So here first what, so we have 1 2 3 4 5 6 7. Okay. So here what we are trying to do, first we will do 2 and 4. First we will perform or 2 and 4. And then what did we have? 2 and 4. Then we have 1 and 7 here. So we have 1 and 7. So now this 2 and 4 and 1 and 7 will together give us what? It will give us Y XOR 3, right? It will give us Y XOR. And then what was the another condition where we have M2 plus M4 plus M3. So if you see this OR gate here will give you M2, M4, and from here we can use M3 to get what? To get Y, right? You'll get Y now because you're already having M2, M4. With that, you're adding M3 together to get Y. So this way, what happens here? How many you're using? You're using 1, 2, 3, 4, 5. And here, how many you're using? You're using 1, 2, 3, 4. So here it might look that you're just reducing one gate, but when you're looking into a larger picture, more real world problems, this makes a huge impact in the output as well. Both cost efficient and also the time. Okay. So yeah, so this way you can implement how different functions, because at the end of the day all the functions can be written in terms of minterms, and once you get all the terms, so if you're having, let's say, A B C D truth table, then which decoder will you use? And you're having, let's say, Y, which decoder, as in it is n is to 2 power n, right? So what is the value of n? Which decoder will you use for?
4 is to 60.
4 is to 64.
Okay, yes. So you will use that. Okay. So you will use 4 is to 2 power 4. Okay. So similarly, yeah. So for each truth table, for each Boolean function, you will make sure that you convert it properly to minterms, and then you can easily convert it to uh, you can easily convert this particular Boolean function using decoder. It's basically implementing that particular Boolean function. So this is with respect to decoder. Then okay. So next will be multiplexer. Next is multiplexer. So before we move on, so for multiplexer, how do you write the general term for it? Like for a decoder, we write n is to 2 power n, right? So for multiplexer, how do you write? Or you can also tell like what do you think a multiplexer is like? What are the inputs, outputs, what is required, sort of things.
I mean, multiplexer, we have multiple number of inputs and we take only one output and we select that output using the select pins.
Yes. So again, the select pin will be your n, and for multiplexer, you usually write 2 is to 2 power n is to 1. You will have 2 power n inputs and 1 output. So we saw in decoder, right? So in decoder, what did we have? 3 is to 8, we had 3. This was enabled. So you had 3, and then you had 8. Similarly, for multiplexer, what you will have is you will have 8 inputs, and then you will have three cell lines, and then finally only one output. So this is the output that we will require. So let's use the same function, that is y xor 3. We can use this same function, and let's say you're having m as 1, 2, 4, and 7, right? So how can you write this as? You can write it as m1 plus m2 plus m4 plus m7, correct? So this one, when you multiply it with 0 or 1, you'll get it. So here what happens? You have m which ranges from m0 to m8. Sorry, m7. You have m which ranges from 0 to m7. So there are all other terms which are 0 and only these terms which are 1, right? So what we'll go and do is we'll just multiply it accordingly. That is 0 m0 plus 1 will be m1 plus 2 again multiplied by 1. 3 is multiplied by 0 and so on. So 4, and then we have 5, 6, and 7. Okay, so here why did we use this is because we are trying to tell that only for these select line, that is M1, M2, M4, and M7, we'll be giving high input, whereas for others, that is 0, 3, 5, 6, we will just ground it. That is 0, we'll just give 0 for that. So now if you're drawing a multiplexer for this, first of all, how many variables are there? How many variables are there? We have 3 variables, right? So what multiplexer you have? You'll have 8 is to 1.
8 is to
Correct. So it is 8 is to 1 multiplexer. So now you have 1, 2, 3, 4, 5, 6, 7, 8. Now here again, always make sure that you're writing the MSB and LSB correctly. And here, so which terms do we have 1 as? 1, 2, 4, and 7, right? So here we will have 1, 2, 4, and 7. So these all terms we will give it as VDD, and other terms that we have 0, 3, 5, 6. So these all terms we will ground it. We will ground these all. So basically these all will get 0 and these all will get VDD. Again, how did we decide it? Based on this, right? So here you'll have 0, 0, 0, 0, 0, 1. So for first term, again we are giving. So based on that, we are giving this and we are selecting the entire output here. And finally, what will you get? You'll get y XOR 3, right? Okay. Now, moving on to a more bigger problem, that is these are for 3 inputs, right? Let's try for 4 input. A, B, C, and D. Okay. Okay, now we are trying for four inputs. So four inputs, let's say. So generally, how is it? Which is easier if you have a four input? Which multiplexer can you easily do? 2 power is 200. So for four inputs, which multiplexer can easily do this? Like easily you get the output just like giving enable and VDD. That is ground and VDD.
16 is to 1.
16 is to 1.
16 is to 1. Now, if we are trying to do this in just 8 is to 1, okay, let me give the output here 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. Something missing here. Okay, there are terms which are missing. Okay, wait, we'll just write this again. Or I have written in the top. Okay, I'll just copy it from here. Okay. So this is for 0. Okay, so for now, if we're having y as let's say 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay. Okay, it is. Okay, it's just a bit diagonal. You can look at it like this. Okay. Okay, so these are the outputs. Now, a easier way to do is to just add 16 is to 1 multiplexer, and you will easily get the desired output. Using what? We will just, let's say this will be your, okay, 0, 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So using this, now if you have to ground it, you will ground 0, 1, 2, 5, 8, 9, 10, 12, 13, 14, 15. So you ground these all, and the all others will have VDD. So using this inputs, when you try to make a 16 is to 1 multiplexer, so you have 16 here, and then so finally what will you get? You will get 1 y. So this is not x. So you will get y. Okay. So again, select lines will be 4. That will be A, B, C, D. So this is the easier way to do. But now if you're trying to just not use 16 is to 1 marks, but we are trying to use 8 is to 1. Okay, so using 8 is to 1. So first thing is 8. If we are using first 8 values, right? So first 8 values here, then the next 8 values can be used in the next multiplexer, right? So similarly, so that is the thing that we are trying to do here. So let's say you're using 8 multiplex. So 8 is to 1, and then you have another multiplexer which again goes from 8 is to 1. So if you see here, this one will be 0. We already have, no? So what do we have? We have 0, 0, 0, 1, 1, 0, 1, 1. So here the 8, 1, 2, 3, 4, 5, 6, 7, 8. So here the values will be 0, 0, 0. Then you have 1, 1. Then you have 0, 1, 1. And then you have your output here for that, for which only the first 8 combinations you have the output. Similarly, for the next multiplexer you will have 1, 2, 3, 4, 5, 6, 7, 8. And what do you have here? So here it will be ABC. Wait, not ABC. So again it is MSB, right? MSB is A. So what will this be? So what will this be if MSB A? Because this is 3. You can just add 3 select lines. So what will this be? Okay, let's just come to this finally. So before that, here also you can come to this finally. Before that, you can just think that the first 8 combinations are given here and the next 8 are given here. So what are the next 8 combinations that we have? We have 0, 0, 0, 1, 0, 0, 0, 0. And again here you have another output. Now finally this output and this output will go here. This is another multiplexer. Here I'll give here 3, right? So we need another select line here because there are totally 4. We have totally 4. The value of n is 4. So here finally this will give us y. So now we try to decide. So which multiplexer is that? This is just 2 is to 1. So now what we are trying to do is we are trying to find out what are these select lines. So you have A, B, C, and D. And you have MSB and this is LSB. So here, which 3 lines do you think this is? Because now if you see this first 8, right? So this first 8, which is the first 8 here? Till here. Till here. So in this first 8, which particular variable is common? Which particular variable does not affect the output at all?
Ma'am, A.
Correct. So A is common. And for the next set of variable, again A is common, right? So what happens? So this first here, the A is always 0. So it doesn't matter whether you're giving that input or no. So here it will be B, C, D. Similarly, here also for this one, the A is always 0. And for this one, the A is always 1. So again here for this particular value you are giving BCD. Now you are getting Y output for A always 1 and you are getting Y output here. Let's just give another variable. Let's say S. Let's say S. So you're getting S output for A always 1 and you're getting S output for A always 0. Now this is where you will try to find out where. So but once you include these two, even these two gets included in the final value of y, right? So once you get complete A with 0 and complete A with 1, you will add that to another multiplexer and then you will use A here. You will use A here. A is 0 or 1. So here 0, here 1. Based on that, that will figure out what to give your output. Okay. Okay, so this is one way of doing it. Okay, so now, so we have already seen 2 ways now. One way was 16 is to 1 multiplexer. The other way is using different, 8 is to the thing is, now we are used 8 is to 1 multiplexer here. Do you think we can also use 4 is to 1 multiplexer? 4 is to 1 multiplexer, is it possible? The number of multiplexers will increase, that's fine, but do you think it is possible to implement using 4 is to 1 multiplexer? Any idea on that? No? Okay. So, okay, so for 8 is to 1, how did we divide it? We divided it based on that A is common, right? A is common here, A is common here. So we used, what did we use? We used two different multiplexer, that is first these 8 and next for these 8. Similarly, if you have to use 4, for 8 you will have 8 combinations. For 4 is to 1, you will have 4 combinations, right? So 4 combinations, 2 power n. So n, what is n? 2. So you'll have two variables in the multiplexers. So if you have two variables in the multiplexer and four inputs, so if you see the first 4 here, wait, let me. So if you see the first 4 here, these 4. These 4 are changing, right? And is A and B changing? No, right?
No, ma'am.
So you can use this 4, right? So this can be done as 1 4 is to 1. And this one will become next 4 is to 1. For all this 4 is to 1, A and B will remain same. So this will be this will be one multiplexer, another multiplexer, then another two more multiplexers you will get. So these all will give you values where A and B are same, right? Similarly, then you will go on to the next part where it will decide A and B. So what happens if we try? We'll not just completely draw it, but I'll tell you. If you're having 4 is to 1 here, so you have 4 4 is to 1. So you have 4 4 is to 1 and you will get all the values. So for this it will be C and D, least significant bit. So you will have C and D for all. So once you get C and D for all these values, A, B will be same. What? A and B will be same. So here if you see A, B will be 0 0. Here A, B will be 0 1. Here again A, B will be 1 0. A, B will be 1 1. So you can use another 4 is to 1 multiplexer, another 4 is to 1 multiplexer, and just give A and B, and all these inputs go in and you'll get Y. You'll get all these inputs here and you'll get Y. But if you want to again divide it into, into 2 is to 1 multiplexers, again what you can do, first have B, because go in the order, same order. So you will have B. So once you get B, that particular output can be given to A. But the easier way is this one. Just use another 4 is to 1 multiplexer and you will totally get the output. Okay. Any doubts in this, like how to use different sets of multiplexers? Okay, then do you think 2 is to 1 multiplexer is possible? So here, is 2 is to 1 multiplexer possible? For the same question.
Uh, yes, ma'am.
Yes, correct. So similarly, what you have to, yes. Yes. Similarly, the same thing. But if you're using 2 is to 1 multiplexer, there will be so many 2 is to 1 multiplexer because it will start with one variable, right? So you will use this 2, and so on. It will keep on going. So moving back to the 8 is to 1 example that we did. here, right? If you see here, we have already used two 8:1 multiplexers and one 2:1 multiplex. But I would like to just use one 8:1 multiplexer, and you can use one inverter. One inverter. You can use this. So for that, what we'll do is, again, we'll write down the table again. So initially, first, let's write down the table again. Is it okay? Can I copy? So here you have 0. Okay. So, and what was your y? 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 0. Okay. So, so again here, right, if I'm trying to group it, okay, if I'm trying to group it, not really group it, but if you see here, these two values here, what do you think it is changed based on? So these all three are same, right? These different, but what is the value? Always 0. So for first, you cannot include the next one because first two look similar, that y is always 0. And if you're using the second two, now what do you think the values are? A, B and C are same and D is different. And what is y based on?
1.
Isn't y D? You have D 0, y is 0, D 1 and y is also 1. Right? So y is based on D. If you see here, A, B, C is same. It does not make any impact on y. But D is the only thing which, that's why we are taking 2, right? We are grouping it to in terms of 2. When you're grouping in terms of 2, what happens is only one particular variable, that is only the least significant bit, changes to 0, 1, 0, 1. So you can see the changes only in the least significant bit. That way, only the D changes and Y is following D. So that way, what will become? Your Y will become D. Okay. So similarly, for the next two, what will be your Y be here? A, B and C, again it's same. And D is 0, 1, Y is 1, 0.
D bar.
Correct. It is D bar. Now, for the next two, Y will be, it's always 1, right? Irrespective of whatever the value is, it is always 1. So first thing you have to keep in mind is, if both the outputs are same, it means that y will always be that. If both the outputs are different, that is when you go to the variable and check y follows which particular variable. Okay. So if you see here, both the values are same, then what will your y be? 1. And here, what will your y be for this?
0.
Hmm. And for the next one?
Will be same D.
Correct. And here y will be 0 and next one also y will be 0. So if you see here, we have brought down y to more simpler terms. That is, we kind of removed D and we bought A, B, C, and y will be 0, D, D dash, 1, 0, D, 0, 0. So again, you have only 8 output. So this way, what will happen? You can easily use just one 8:1 multiplexer. Okay. So let's draw the multiplexer 8:1. So 1, 2, 3, 4, 5, 6, 7, 8. So what was the value that we had? We had 0, and then we are giving out input D here, because here D, right? So D. Then next is D dash. So that is why we are using an inverter. We go and we give D dash, and then we have 1 0. We have 1 0. Then again we have D. Then again it was 0 and 0. So what are the select lines that we used here? So when we grouped it into two, which was the variable was changing? Which variable was really changing? D, right? Only the D, that is the LSB, was changing. What was it changing? It was changing 0101. Change as in nothing big change. The usual binary changes were happening. Whereas when you grouped it into two, all the three variables were constant. So that is why at the end you have Y in terms of D. You have Y in terms of D, right? So if you see, you have D terms as Y inputs. So if you have already bought D as Y inputs, so what are the three variables that should be given as select lines? Are you able to understand what I'm trying to tell, or do you have any doubts in this? Yes, it is ABC. It is ABC. Why? Because we have already brought D into input here, right? We have already made Y in terms of D. So if we have made Y in terms of D, what are the values which should be used to select? It should be ABC, because you're already giving D as an input here. So finally, you will get an output based on that. So that's what I told you here, that wherever it's constant, the same thing we did here, right? Above, whichever was constant, we left it, and finally we used it. Similarly, here also we used the D initially, and finally we are using these all three variables the same way, the same kind of thing we used before for the multiplexer. So this will be your 8:1 multiplexer. Okay, so any doubts in this topic? Anyway, you didn't understand anything, like how to use multiplexer, implement, or a decoder? Any doubts? If no doubts, we can move on to the next topic, that is lookup table. So I'll give you a brief on how to use like implement the Boolean function using lookup table, and the rest we can see in the next class. Okay, any doubts, or can we move on to the lookup table? Can? Okay. So lookup table, so implementing the Boolean function using it. Okay, so first thing you have to remember is there is a decoder. There is a decoder. N is to 2 power n, with select lines which moves all the way from A0 to AN minus 1. So A0 is LSB, AN minus 1 is MSB, most significant bit. And then you have an enable signal which is given to VDD. And finally, there is a table here in terms of rows and columns. So let's say there are many rows and many columns. Okay. So first, if you see, this is again the LSB. and this one will be your MSB, be k minus 1. And here you have your value from 0 to k minus 1. So I will let you know why we are using this particular lookup table and how to use it. So again, you have here how many? You are having 2 power n. So all this 2 power n will be connected this way here. Okay. So if you see how this will happen is, so this decoder here, right? So this decoder here, it will turn on exactly one row. It will exactly turn on one row at a time. So if you see here, there are many outputs, and each output is connected to each row. So this decoder is responsible to turn on only one particular row at a time. So we've already seen the example of XOR 3, right? So we will use that. So what was it? It was 2, 1, 2, 4, 7. It was 1 to, your minterms was 1 to 4, 7. So if we use the same thing here, what will happen is, first I'm having a decoder. So it was for 3 input. So it will be 3 is to 8 decoder. Okay. It will be a 3 is to 8 decoder with an enable with it. And then you will have row. And this row, what is this row? This row, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So for this row, this will give you the y. So what was your y XOR 3? It was 0, 1, 1, 0, 1, 0, 0, 1. Okay. And here each input will go to the respective table here. It will go to the respective row. So what we are trying to tell is, this decoder here, it is responsible. This decoder here, it is responsible to switch on exactly one particular row at a time. And how this decoder works, what will be the select lines here? A, B, and C. So based on this A, B, C, it will go and select one particular row at a time, and this is what we call it as B naught. And finally, this will be your Y XOR 3. So it's basically a table. If you see as a whole, the idea is it is basically a table, and your decoder is used to fetch the value from that table. So that exactly gives you why the name is, right. The name itself is the lookup table. You have a table with the y values there, and you're finally using it to find it out. So similarly, if you're having many outputs, right? So we saw that at the same time multiplexer we were able to do y XOR 3, and then we have another y. So we use these together to perform in the same one particular multiplexer. So similarly here also, this table can be extended. It can have many rows, and columns will be based on, it can also have many columns. So based on which particular in the output that we get from the decoder, right, that particular row will be given to us. So if you see y, what was the y which we initially had? It was 0, 0, triple 1, triple 0. Okay. So it is 0, 0, triple 1, triple 0, and this will give you b1, and that is none other than y. So if you have another, let's say another output, even that can be given here, and even that will be added. So the same thing happens. You will have three variables, and these variables will work on 0, 0, 0, 0, 0, 1, and so on. So based on this, and if you see, you're having enable sign here, right, to get the particular respective output. So based on which particular output is required, that output will go and fetch the table that is here, and it will give you the output. Okay. And finally, this entire row will be your y XOR 3, and your b1 will be y. Okay. Okay. So the main idea for all this is right, like it's just to program the logic differently. Like if you see the lookup tables, the main idea here is like you use a decoder to select that particular row and give it back. Similarly, if you see multiplexer, you can use different kinds of multiplexer to implement the Boolean functions. So each time you, so why we learn different kind of things is like based on your problem statement, right, you will be able to understand, right, which will give you a better output, not just in terms of answer but also in real world. You also have to consider how efficient it can be done, how not just time efficient, even cost efficient. So these all efficiency will play a huge role in how you select which particular method you go ahead and solve your problem with. And before we close, I think we can just we can look on to signed and unsigned binary addition. So this is a very small topic that we have. So we have signed and unsigned and signed addition. Okay. Okay, again binary. We are just talking about binary now. Okay. Okay, so let's say you have two n-bit numbers. If you have a two n-bit numbers, A, B, okay, let's take 8-bit. Let's take 8-bit. Then that will range from A7 to A0, B7 to B0. Subsequently, what we will do is this term, right, the 7, that will be considered as most significant bit. And this term here, 0, that will be considered as least significant bit. So starting with unsigned addition. So unsigned as in you don't have whether it is a positive or negative number, and it's always considered positive. So if you have two terms A, B, and let's say I'm giving 0, 1, 2, 3, 4, 5, 6, 7, and then you have 0, 0, 1, 2, 3, 4, 5, 6. Okay. So can you tell me what are these two values in terms of binary numbers? Sorry, decimal numbers. Yes, so did anyone get? Okay, yeah. One 28 and 64. Okay, so I did not solve this. I'm hoping that it's correct that you told. Okay. 64. It is not 64 and 32 for sure. I think it's 128 and 64 makes more sense to me. Okay, so now let's say we are adding this to, okay? adding the, okay, let's just add the decimal now. So if you add these, sorry, so if you're adding these two numbers, what will be your value? 192, right? Similarly, now we are trying to add binary addition. So for binary addition, if we add 0 0 0 0 1 1 1 0 will be 1, and 1 plus 1 will be 0, but carry will be 1. Okay, and if you have 1 plus 1 plus 1, 1, but the carry will be also 1. Okay, so because binary, it cannot exceed above 1. So the next term will become carry. So now we have 1 plus 1, which will be 0, and my carry is 1. 1, 1, 1. It is 1, carry 1. 1 1 1. It is simple. It is like, even it's simple if you take in terms of, let's say, what is 1 plus 1 plus 1? 3, right? So 3 in terms of binary will be, what is 3 in terms of binary? What is decimal number 3 in terms of binary? One 27 and 63. Okay, so now it is 127 or 128? 190. So it's 127 and 63.
Yeah, I think 127. It will be an odd number since 1 1 is 3, 1 1 1 is 5, 7. So 7 ones will be 127.
So this way, if you see 1, it can be written in terms of 1 and 1, right? So if you have 1 and 1, what did you normally, if you have two numbers in your regular addition, your decimal addition, you'll just carry the other number to here, right? Same thing for 1 and 1. If you have, you'll just add right one here, the other will go carry. Same thing, triple 1, again 1. This will be again 1. This will be again 1. This is again 1, and 1 plus 1 will give me 0, but carry 1, so this will be 1. So now we got this number. So let's check this number if it is equivalent to this decimal number. So can you try what? So this is unsigned number. You can just try to convert it into decimal and let me know. What should this be? This will be 28, 32, 16, 8, 4, 2, 10, 30, 62. Okay. Yeah, so 190, correct? Yeah. So it is 190. So we got the same number, right? So yeah, so this is for unsigned number. And so yeah, so for the unsigned number. Similarly, I just before we end the class today, I just wanted to let you know two maximum numbers. That is, let's say for a 8-bit, I'm having 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So what is this number in decimal? 255, right? Normally for 8-bit number, the range will go from 0 to 2 power n minus 1. So it will be 255, right? This is also 255. So what is 255 plus 255? You will have 10, 5, 10. So is it possible to denote this in 8-bit terms? That is, if in 8 bits. So if you're trying to add this here, what you'll get 1 plus 1, 0 and 1. So the now rest numbers will be 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and carry here. It will go to the next one. No, it will go to the ninth bit. So we know that the maximum, if you're adding the maximum two numbers of A and B, if you're adding the maximum two numbers of A and B of 8 bits, it cannot be added within 8 bits. It will overflow to the next bit. It will move on to the ninth bit. Okay. So, uh, so yeah, you can keep this in mind for now, that whenever you're adding the two number, and not just the maximum number, even if you had, let's say, 253 and 255, it will still exceed, right? It will still, because your range of your 8-bit number is just this. It is within 0 to 2 power n minus 1. So it will still exceed the maximum value of the 8 bit. So that way, overflow occurs, and only at this point we will introduce like sign extending and adding. So at this point we will extend sign extending and adding. So okay, so regarding the sign extending and adding, and also for sign numbers, we will look into it in the next class. So just let me know, do you have any doubts from today's class, like Boolean function using decoder, multiplexer, lookup tables, and unsigned addition? I think it's pretty direct, because I hope that you have already tried it till now. So apart from that, like, any doubts? Okay. So if you don't have any doubts, then we can continue the rest of the summary in the next class, Wednesday, and we can look into the problems later. Okay. Okay. If there's no doubt, then we'll close the session for today. Thank you.
Thank you, ma'am.